Hello everyone. This is Cullen from Scholarly, and today we're going to be going through the 2022 mathematical reasoning question paper for the selective school test. So, if you're just looking for some extra clarification on some questions you did, or if you've done this full paper and you're looking for a step-by-step solutions, you've come to the right place. So make sure that before you watch this video, you have attempted the test and you've marked your answers, just so you can know where you're sitting, what questions you're actually particularly looking out for, and without further ado, let's get into it. So there's 35 questions, 40 minutes, so that should give you an idea as to how long you should be spending on each question. And let's just get started going through the questions, and I'll probably put some timestamps as to each question or each group of questions so you can navigate where necessary. Okay, so question 1. 3 packages are weighed together. Their total mass is shown on the scale, and that looks to be in between 2 and 3, so that looks to be 2.5 kilos, or 2,500 grams. Remember, if you want to go from kilos to grams, you just times by 1,000. Okay? Now, package 1 has a mass of 850 grams, and package 2 has a mass of 225 grams. What is the mass of package 3? Well, if we find the mass of these two together, package 1 and 2, then we know the total mass is 2,500 grams, so we can just subtract to get the mass of package 3. So let's work that out. Package 1 plus 2. Package 1 plus 2 is going to be 850 plus 225. So just working that out. So we get 1,075 as the mass of the combined package 1 and 2. So to work out package 3, we literally just need to subtract to find the difference between the total and those masses we just worked out. So the total being 2,500, the masses we worked out being 1,075. Let's borrow from this 5, and borrow from the 10. And so we get 10 minus 5 is 5, 9 minus 7 is 2. And finish it off. So the answer we get is 1,425, or option C. Okay, so just finding the difference between packages 1 and 2 and the total weight gave us package 3. All right. Question 2. At a garden shop, Claire is packing plants into boxes. Each box holds 6 plants. One of these boxes here. She has 149 plants and she wants to fill 27 boxes. How many more plants does she need? Well, first of all, we should work out how many plants she would need in total. Then we can work out how many more she needs. So 27 boxes with 6 in each box, 6 plants in each box. We can work out the total number of plants by doing a multiplication. We're looking at, 27 groups of 6. Okay, so 7 times 6 is 42. 6 times 2 is 12. Plus 4 is 16. So you get 162 plants. Now she already has 149. So to work out how many more she needs, that's beckoning us to do some subtraction, and so we need 13 more plants. Okay, and so option D there is going to be our culprit for this question. All right, so question 3. The diagram below follows these rules. Multiply the number in the square by 4, multiply the number in the triangle by 3, and then find the difference between these two results and write it in the circle. Okay, so we know that the number in the square is greater than 1. Okay. And so basically the idea with this is all these ones where you have a stepwise process like this, go to this step, go to this step. The best way to find out the original or the number in the square is to work backwards. All right. So what we're told is the difference between the square and the triangle numbers after multiplying them by their respective numbers is going to be 14, because it's going to be the number in the circle. All right. So this is the difference. Now, 2 times 3 is 6, so it's the difference between 6 and whatever is in the square after we've multiplied. And we know that since the square is more than 1, that it has to be 20, okay? Because that will create a difference of 14. See here? 20 minus 14 gives you that 6, all right? So, the square after multiplying, so this whole diagram here is after multiplying, will have a 20. So what is it going to be originally, or before multiplying? Well, we have to times by 4, and what times 4 gives us 20? That's right, 5. So the answer is going to be 5. But with these kind of questions, you can always check each answer to see if it works, right? So let's just check our answer just to make sure it works, and I can show you it you can do this if you're not sure how to work backwards. So let's see, if we put a 5 in here, and we know that the triangle has a 2, let's follow the rules. Multiply the number in the square by 4, okay, that gives us 20. Multiply the number in the triangle by 3, that gives us 6. Find the difference between these two results, and write in the circle, that would be 14, and so we see that that lines up nicely. Okay, so option C there is the answer. You can either work backwards or test out each option. Question 4. Raina, Penny, and Joshua share a pizza. Raina eats 2/10 of the pizza. So we can notice here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've divided this pizza into tenths. So 2/10 of the pizzas would just be 2 slices. Alright, so Raina eats this much here. Alright, so let's make Raina black. Penny is going to eat 4/10, so that's going to be 4 slices. So 1, 2, 3, 4. These ones here. Alright, and now Joshua, who's going to be purple, eats 2/5 of the pizza. Now 2/5 in terms of tenths, right, is going to equal how much? Well, you need a times by 2, so you get 4/10. Alright, so that's actually going to be the remainder of the pizza. 1, 2, 3, and this last one here. Alright, so Joshua has eaten 4/10 of the pizza. So let's just write down 4/10 just so we don't forget. Which of these statements is or are correct? They eat the whole pizza. That is correct. Joshua eats the least pizza. That is not correct because he ate the most, or the equal most, being 4 slices. And Penny eats twice as much pizza as Joshua. No, this is not true either. So the only correct statement would be statement 1, that they ate the whole pizza together because they ate a total of 10 slices, and there are 10 slices in the pizza. So that question there is option A. Alright, moving on. So, question 5. Which of the following calculations shows how to work out the number of seconds in 24 days? Well, there are 24 hours in a day. Alright, so if we want to find the number of hours, we would have to times this number by 24. Okay, so we're going to be doing 24 times 24. This gives us the hours here, after we've found that. Then we want to go into the minutes. So we've got to times by 60 because there are 60 minutes in 1 hour. Right? So to find the amount of minutes in this number of hours would be times by 60. Okay. And then we want to go to the number of seconds, which is our final number. And there are 60 seconds in a minute, so we'd have to times by a further 60 seconds. Right? So we need to have 24 times 24 times 60 times 60. And the only one that fits that is going to be option E. Okay. So just step by step through it. Write out what you get at each stage, hours, minutes to seconds, what calculation you need to do accordingly, and hopefully that will make your answer fall out nicely. Okay, question 6. There are a total of 160 children in 6 classes in a school. Column graph shows the number of children in classes 1 to 5, and the column for class 6 has not been drawn. There are 30 children in class 3. Okay, so we know that this here, class 3, is 30. Alright, so let's work out first of all what these markings are. Okay, so if this is 30, we can see there that this would have to be 20. Alright, this line here, because you can see the bold, slightly bolder lines, they're exactly 5 lines apart, and this would have to be 10 here. Okay, and so we can see that in between, there's 5 notches in between each thing, so that could be a perfect way to do up by 2s. Okay, so this will be 20, 22, 24, 26, and 28. So now our job is to just work out how many students we have. We know that the total is 160. We can then accordingly work out what class 6 would be. So, class 1, 20 students. Class 2, 28 students. Class 3, we were told, is 30. Class 4 has 26, just lining it up with those lines. And class 5 seems to have 24. Alright, so if we add all these up, 20, 28, 30, 26, 24, let's just add them up. We can work out how many we have so far. So 8 plus 6 is 14, plus 4 is 18. 1 plus 2 is 3, plus 2 is 5, 8, 10, 12. Okay, just adding all those up. So we get 128 so far. Alright, so that means that class 6 has to have the remainder. Alright, and so 128 plus what gives us 160? Well, we'd need to do 160 minus 128, which would give us 32. And so the answer there is going to be option C. Alright, so good stuff, you got that one. We just needed to add up all of these columns, basically. Okay? Now, question 7. The total mass of the objects on the left side of the balancing scales is the same as the total mass of the objects on the right. Every triangle has equal mass, and every square has equal mass. Now, if the mass of a triangle is 6 grams, what is the mass of a square? Alright, so to do this one, we should first of all work out the fact that, okay, so this is 6 grams here, right? And this is going to be 6, 6, 6, 6, okay? So what we have really on these scales is 24 grams, right, on the right side, because there's 4 triangles, plus a square, right? And this is balanced with a 6 and 3 squares. Okay, so it's just 6 grams plus 3 squares, okay? Now, I suppose the way we can think about this, we can solve this as an algebraic equation with a squares or an x's, right? Or we can think about it like this, in the fact that, okay, well, we've got, let's just get rid of one triangle from each side, right? If we do the same to both sides, okay, then it doesn't change the fact that it's balanced. So if we got rid of one triangle from each side, okay, that would remain balanced. Now, how about we get rid of one square from each side as well, and that would also remain balanced, all right? So, what that has told us now, if we got rid of one triangle and one square, we are left with, on our balancing scales, we are left with 2 squares on this side, right? And we're left with 3 triangles on this side. Okay, so what that tells us is that since this weighs 18 grams, 3 times 6, right, that these 2 squares has to equal 18 grams, okay? And so that means that each one would have to equal 9 grams. So you could either do that by logically removing a block from each side until you have something that's directly comparable, or by solving this equation here that you've created, okay? And by that, you would, we'd say, okay, well, let's take away a square. You're kind of doing the same thing. You're taking away a square from each side, okay? So you have 6 plus now only 2 squares equals 24, okay? And then from here, you say, all right, well, let's take off 6 from each side. As long as you do the same thing to each side, it's fine, right? And so that leaves us with 2 squares equaling 18. And we actually have the same kind of calculation as we had in the other method. Okay, so it's kind of actually doing the same thing, just a bit more of a visual approach as opposed to a mathematical one. Okay, so the answer there is going to be D, 9 grams. All right, so hopefully that is making sense. Let's move on. Question 8. The table shows the exact times taken by 5 racing drivers to complete 1 lap of a motor racing circuit. Okay, so we've got all the times here. Who are the fastest 3 drivers in order, starting with the fastest? Well, first of all, we've got to look at the first decimal place. We can see that this one has a 0.0, so they're going to be clearly faster than all the others. We want, remember, a lower time equaling faster. Right, so don't mix it up with trying to find the highest number. So this one's the first place. Okay, the next we've got someone with a 0.1, which will be obviously less than all the 0.2s and the 0.3s. Okay, and then the third person would have to be one of these two. Can't be the 0.3. So you can see that this one here is technically the same as going 0.200, sorry. Whereas this one's got an 8. So this one's slightly higher, meaning it's slightly slower than Batra. Okay, so Batra is going to be the third place. Okay, so just look at the first decimal place, and when they are the same, in this case, 2 and 2, look for the next ones and see which one's higher. All right. So we have first place being Adams, just only these two. Second place being Smith, yep, and then third place being Batra. So that gives us option E. Alrighty. Let's keep on moving. So, option E for that question, question 9. A boy is standing at point P, facing east. Alright, let's try east. Okay. He turns clockwise to face a house which is pointed at H. Okay, so he's turned clockwise, meaning going this direction, to face H. Alright, we need to find the angle of his turn, which is going to be this angle around here. Okay, so we can fill in the gaps. We know that between north and east, that's going to be a 90-degree angle. Alright, because it's just a right angle there. Now, the total circle, right, if you go all the way around from north, all the way back to north, that's going to be 360 degrees, right? So that's one revolution. So we can pretend, what if we went all the way around, right? We should get to 360 degrees. But we've already got some of that covered, all right? We've already got a 60 here, and we've already got a 90. All right, so in order to work out this angle here, this green angle down the bottom, all right, well, let me make it a different color so it's different from the 90. This orange angle down the bottom. In order to work this out, we basically take 360, because that's the whole revolution all the way around, and then minus the bits that we already know. 90 and 60, right? So if we minus 90, we minus 60, right? That's the same as minusing 150, right? Because you just add these together and then minus the results, right? So 360 minus 150 is going to give us 210 degrees, okay? And so we can see here that this would have to be 210. Let's just verify it, make sure it all adds up. So 210 plus 90 plus 60, well, 210 plus 90 is 300, plus 60 is 360. So we get a nice, beautiful 360 degree revolution all around, with that orange angle being 210. So the answer there is option D. All right, again, make sure with your angles, take note of some known facts that you can use that aren't obvious in the question. So here you had to use that 360 degree fact in order to understand how that works, okay? So good job if you got that one. Question 10. Alex had $76. He spent some of it in a shop. Then he gave half of what he had left to Charlie. Charlie spent a quarter of what Alex gave him on lunch. Then Charlie spent $9 on lunch. Okay, so the job here is to work backwards, basically. Okay. Again, as I said, with all these things where it goes in a stepwise fashion, the best way to kind of get back to an earlier step, given some information from a later step, is to work backwards. So if Charlie spent $9 on lunch, and that $9 was a quarter of what Alex gave him, right? So if $9 equals a quarter of what was given, right, quarter of what it was given, then the whole thing is going to be 36, right, times by 4 to get the whole thing. So he was given $36, right? Because a quarter of 36 is 9. So that's that first step done when we're working backwards. So we've got back to here. So Charlie spent a quarter of what Alex gave him on lunch. We've done that step. Now, Alex gave half of what he had left to Charlie. So 36 is half of what he had left. Half of leftover, right? So then the leftover, if 36 was half, it's just got to be double. So 72. Okay, so 72 was left over. Now, if he originally had $76 and left over is 72 from what he spent on the shop, then you can see that he's only spent $4 because that would bring us down to $72. Okay, so the answer there is going to be A. He spent $4 in that shop. All right, and that is question 10. Question 11. A rectangular prism is made from identical small cubes. Each small cube is solid and looks like this from the side. Okay. So you can see here that this is a single cube. Right? So one little square is a single cube from the side. The three diagrams below show three different faces of the same rectangular prism. Okay, how many small cubes is the rectangular prism made from? Now, it doesn't really matter how we construct this, okay, as long as we make sure that the lines line up. So, for instance, right, you can see here that we've got 1, 2, 3, 4, 5 cubes along the top, meaning we need to match this with a different face that has also 5, which corresponds with this one. All right, so we want to put this face up here on the top. So let's treat this as the side. So when I say it doesn't matter, I mean which one is the side, which one's the top, which one's the the back or the bottom, right? So let's treat this as the side, and we can construct our shape around it, right? Since this is 5 in length, this one here, we can put it alongside here. So that would be a 2 by 5 little construction there, right? And so you can see that that's that exact shape on top. Okay, so this one is done. The last one is 3 by 2, and that lines up with if we put a shape here, right? Because that's 3 high and 2 across, right? And so you can see that forms our rectangular prism. All right, so just to clarify one more time, this is the face shown here. You can see that that's the exact same number of cubes, and that this is the face shown here. Okay, now we need to ask how many small cubes is the rectangular prism made of. Well, why don't we divide this into the two faces, or not faces, but the two kind of halves. If I halve it like this way, so that I have just what's in purple, because you can see that then behind it is the exact same shape, right? This is the exact same as what I've just covered in purple. So, within this purple, we have 3 by 5 cubes. We have 15 cubes in this front half, right? And in the back half, you'd also have 15 cubes. So, together that gives you 30 cubes. Right? You can count this any way you like. You can do it counting rows one at a time. If you look at the top row, right, that's 5 by 2. So that's 10 in the top row. So then 20 once you add the second row, and 30 once you add the third row. So many different ways to add it up. Just count up the cubes in any way, systematically, by either picking a row or a face or whatever, right? And so we get 30 cubes, and that is option B. Alrighty, so let's move forward to question 12. Jennifer sells bunches of flowers. She wants to make a picture graph to show the data in the table. Alright, we've got Monday 24 flowers sold, Tuesday 28 flowers sold, and Wednesday 36. She wants to use these pictures only in her picture graph, and she will not draw any other fractions. So she's not going to draw a quarter or, 3/4 or a third or anything like that, okay? So we're given some options as to how the key could be constructed, where as a flower represents 4 bunches, meaning half a flower, I'll just draw a rough version of half a flower here, would have to equal 2 bunches, okay? And then, so if we have a look at the other ones, if that flower represents 8 bunches, then the half flower would represent 4. And then if it represents 12, we'd have to have 6. Okay, so we need to work out which of these is plausible to use, given the multiples of the numbers. So, first of all, let's start with key x, which is 4. Let's see if these numbers are divisible by 4. They all are. So this would just be like 6 flowers. This one would just be 7 flowers. And this one here would just be 9 flowers. Okay, so key x can clearly be used. All right, we don't even need any half flowers. All right, now key y represents 8 bunches. Well, let's have a look first of all. 24 is divisible by 8, so that one's no problems. So divided by 8 gives us just 3 whole flowers. Now 28 divided by 8, well, you'd have 3, remainder 4. Okay, because it goes into 24, and then you have an extra 4. Now, would this work? Yes, it would, because we'd have 3 whole flowers, right? I'll just draw circles. 3 whole flowers, and then a half flower, because a half flower is 4 in this key y, right? So this works. Let's have a look at 36. If I divide 36 by 8, the nearest multiple is 32. So that would be 4 remainder 4 as well. Alright, so you'd have 4 whole circles and then a half circle. So this key works as well. Okay? So yeah, just make sure that you can have the half flower and you don't need any other fractions. Alright, half flower being 4. Okay, so as long as the remainder is the same as the half flower, that's fine. So 8 works. So key y is also working. Alright? So key z, 12 bunches. Let's have a look. 24, this would be fine. This is just 2 whole flowers. 36 also, this is just 3 whole flowers. And 28 though, what's the nearest multiple of 12? Well, that would be 24. So it's 2 remainder 2 remainder 4. But this doesn't work because we have half a flower being 6. There's no way of us representing a remainder of 4. So key z unfortunately cannot be used. Alright, so then our answer is going to be key x or key y only. Alright? So the remainders for key x and key y lined up. The remainder for key z did not. We had a remainder of 4 when we need only remainders of 6 in order to keep it to only whole flowers and half flowers. Alright, so that is question 12 done. Question 13. 3 different numbers are chosen from these 4 numbers. They're then added together, and which of these statements are correct? Okay, so we've got some possibilities. Total cannot be multiple of 8, total can be a multiple of 3, etc. I think the best way to do this is there's only 4 possible combinations. Think about it, right? If you are adding up 3 different numbers, you can leave out 1 different number each time. So we could have 3 plus 5 plus 6. We could have 3 plus 6 plus 8. We could have 3 plus 5 plus 8. And we can have 5 plus 6 plus 8. Those are the only 4 combinations. I think the best way is to just look at these totals, right? And then see which of the rules is satisfied, which is not. So 3 plus 5 plus 6 gives us 14. 3 plus 6 plus 8, 17. 3 plus 5 plus 8, 16. And 5 plus 6 plus 8 gives us 19. So the total cannot be a multiple of 8. Well, we see we have a multiple of 8 here. So it can be a multiple of 8. So statement 1 is wrong. Total can be a multiple of 3. Well, I don't see any multiples of 3 here, so that's wrong. And the total is always odd. Well, we have 14 and 16, so that is also incorrect. Alright, so it seems as though the statements that are true are none of them. Option A. Alright, and that is question 13 done and dusted. Question 14. The diagram shows a triangle inside a rectangle. The area of the shaded grey area is 84 centimeters squared. What is the area of the triangle? Well, if we want to find the area of this triangle here, we can find the total area of this rectangle, right, this whole thing, and then simply minus the grey shaded area. Okay, so to find the area of the whole thing, we're going to do length times width, which is going to be 12 times 11, right? Giving us 132 square centimeters. All right, now the area of the gray shaded area, all right, so this gray area around the outside, all right, is 84 centimeters squared. So to find that triangle, or the purple area that I've colored in there, we just subtract. We just do a subtraction. The total minus the gray. All right, so we just do 132 minus the gray shaded area, 84, and we get, let's see, we get 48 centimeters squared, okay? And again, you can just check. Now, I always recommend, if you have time, to just quickly check if this lines up. So if the triangle is 48 and the gray shaded area is 82, let's just add them up, make sure it adds up to 132, and you can see, sorry, 48 and 84, and you can see that there we have 12, and then 1 plus 4 plus 8 is 13. So we have 132 here, okay? Apologies for writing 82. But yeah, we can see that this lines up. The 84 plus the 48 that we circled gives us the correct total area of that rectangle. All right, so that is question 14 done and dusted. Question 15. Seojung has been recording rainfall for the last 5 weeks by collecting it in a container. The container was empty at the start of week 1. Seojung recorded the amount of rain in the container at the end of each week, no water lost during the 5 weeks. So, we're seeing that we're only adding water each time. No water was lost. So it's not like we got 100 mils at the end of, during week 2. We had, however much we had in week 1, that looks like maybe 60, and then we had an extra 20 in week 2. That's the idea here. And that can possibly trip people up. So, during which 2 weeks were there exactly the same amount of rainfall? Okay, so we've got to work out the amount of rainfall in each one. Notice how it goes up again in those 5 increments, 1, 2, 3, 4, 5. So we can see that this would have to be increments of 20. All right, we can work out each thing accordingly. So here we have 60 mils of water. Here, we're adding on an extra 20 mils of water. Now here, from 100 to 180, we're adding on 80 mils. From 180 to 220, we are adding on 20 mils. So we can see here, end of week 2 and week 4, we actually have the exact same amount of rainfall. Okay? So option D there is going to be the correct answer. All right, so just make sure you look through and you see which ones. Don't get confused by the fact that they're all different. It's because we're actually adding the amount. It's cumulative, is what we call it. All right, and this last one, just in case we were curious, from 220 to 360 would be plus 140 mils. Which clearly doesn't line up with anything. Okay, so we can see week 2 and week 4 is our answer there. All right, question 16. Brody is thinking of a quadrilateral. The quadrilateral has no parallel sides. The quadrilateral has 2 sides of 5 centimeters and 2 sides of 8 centimeters. Okay, and it has exactly 1 right angle. All right, so if we're trying to think about this, right, how many lines of symmetry does Brody's quadrilateral have? Well, let's try and construct this quadrilateral, right? If we have a right angle here in the corner, no parallel sides, okay, so I suppose no parallel sides, you can do something like this, and then you need, something like this, okay? However, think about it like this, right? These sides need to have equal lengths, okay? So the only possibilities that I can see are the idea that both the sides around the right angle would have to be 5 centimeters. That's one possibility, okay? In which the sides of 8 centimeters would have to be the exact same length and meet at the exact same spot, like a kite almost. Right, so for them to be the same length, you'd almost form a little isosceles triangle here, between here. And so this actually gives us 1 line of symmetry. Okay? There's no other line of symmetry here. So the answer would be 1. But let's have a look at another possibility in which we have 5 centimeters on this line and we actually have 8 centimeters over here. Right? Is it possible for us to fill in the gaps and have 8 centimeters here and 5 centimeters down here? That's actually not possible because the only way we could do that is by forming a rectangle, right? Having 8 centimeters. Because the only way you can get from 5 centimeters from here to somewhere else would be directly through that point, or anywhere around this kind of radius of a circle, but the only way where it's going to be 8 centimeters to that point is going to be at that point. And we're told we can't have any parallel sides, so this one would fail that test, all right? and there's no other way to form this quadrilateral. So basically just construct, if you see a contradiction with the question, e.g. like parallel sides, also this would have more than one right angle, so you can see that that's kind of a problem. Because if we tried to send these 8 centimeters sides and 5 centimeter sides in different directions, it just wouldn't be the right length. Right? If I made an 8 centimeter side up here, it would be more than 5 centimeters to bring it back down here. Alright? If I made an 8 centimeter side like this, alright, let's say, or maybe something like this, right? Then it would be less than 5 centimeters to bring it down to here. The only way that you can get that sweet spot where it would be 8 centimeters and 5 centimeters is having a rectangle, and that would break the rules 1 and break the rules 3. So the answer here, based on our diagram, you can see there is one line of symmetry through this kite, which satisfies all the rules. Also, given the fact that this is a possible, right, definitely a possible structure, and we only are giving one answer, right, you can almost do this, get this answer, draw this structure, and see, okay, well, if there's only one answer and this one has one line of symmetry, then any other possible layouts would also have to have one line of symmetry, okay? Because you can see one line of symmetry is the correct answer for this one, and you can't circle more than one answer. So, as long as you find at least one example, make sure you keep that in mind for all types of questions you encounter in the future. As long as you can see one example, and there's only one answer, you can see one example gives a certain answer, you know that that's probably going to have to be the answer, okay? So, that's question 16. Question 17. A gardener has a box of bulbs to plant in a garden. The garden has 3 sections. She plants half of the bulbs in the first section, 3/4 of the remaining bulbs in the second section, and she has 6 bulbs left, which she plants in the third section. Okay, so our job here is to work out, first of all, how much the 6 bulbs, like what fraction this is, okay? And I often find when we're dividing something into fractions, I think using like a circle and using like almost like a pie chart layout to do this is probably the best way and the most intuitive way to look at it, okay? So let's have a look at this circle. So half the bulbs were used in this first section, okay? So half of them are gone. Now, she said 3/4 of the remaining bulbs, okay? So if we get 3/4 of the remaining, well, the remaining here is a half. And so if we divide this into quarters, we're really dividing the whole circle into eighths, if that makes sense. So we divided this into quarters, all right? And we're really dividing the whole circle into eighths, because if you see, if we replicate the same size of sections, we'd have eighths, okay? So, then we have 3/4 of this remaining section, so that would be 1, 2, 3 out of the 4. So we're actually left with, so this would be our 6 bulbs in here, and we're actually left with this being 1/8 of the total, okay? So, using the pie diagram can often help you. You could also, work out 3/4 of 1/2, work out how much that is in terms of that, so that's 3/4 times 1/2, giving you 3 on 8, right? So we've used half already, we're plussing 3 on 8, and then you can kind of do that to work out that you've already planted 7/8. That can tell you you've got 1/8 left, that's another way of doing this. But anyway, either way you do it, hopefully you get the same answer, that you have 1/8 left. And so the 6 bulbs equals 1/8. So in order to find the total, you just got to times by 8. Alright, so if 6 is 1/8, times by 8, times by 8, we have 48 bulbs here. Okay? So, the answer there is going to be E. The original number was 48 bulbs. Alright, question 17. Done. Question 18. A cube has been painted around one vertex as shown. Which of the following diagrams could be a net for this cube? Alright, so I think the purpose of these ones is to try and fold them up in the way that would make sense, alright, and see if it creates the right cube, rather than trying to unfold the cube and work that way. I think it's better to try and fold them up. And so whenever you're trying to fold something up, pick something to be the bottom, something logical to be the bottom, and then fold everything around it. So this is going to be the bottom here. This is what I'm picking as the bottom. Don't have to, but I'm going to. Now, if I fold this up and fold this up, we're left with, right? We're left with that corner having, one sticking up here with a blue in the corner like this, right? And then the other one also. So this is my bottom here. I'm kind of drawing this a little bit roughly just so you guys can see. And then this would also have a blue in the corner here. So that's actually so far so good. On the outside, you'd have the right amount of blue on this corner and this corner, right? Now, the other side doesn't matter. We're folding up onto this side here. So we'd have like this shape here. And then the back as well, you fold this up once. So you get the plain one there. And you're folding this over the top. Right? So imagine now, it's difficult for me to do this just on the 2D paper. But you can really imagine folding this shape over the top. And you would see that once you kind of fold that over and flip that over, the actual shape you're getting is mirrored. So the actual shape you'd get when you fold over is something like this on the top, right? Imagine folding it over and you get that kind of triangle at the top. So that lines up perfectly. We have the two triangles done on the side, and once we pop something on top with that right triangle just in the corner there, we've satisfied this one as well. So actually, diagram 1 works. All the triangles are oriented correctly. We got the two side ones. They're oriented correctly such that the triangles are pointing inwards at each other, like here, this, and this, right? And then the top one came, and we got that triangle facing inwards. So we got that nice shape there of the vertex. So diagram 1 works. Alright, so it has to be these ones. Now, diagram 2. Let's do the same process. Let's treat this as the bottom here. So we fold this shape up, so that gives us a kind of face looking at us that would be somewhat like this. Right? So that would be when we fold that shape up. Now, this one here is going to go around the side. Okay. So imagine once we folded this up, these two are now kind of hovering vertically. Just imagine if I took this as a piece of paper and folded this whole kind of 3 section. These are connected, so we can't disconnect them. Fold this whole 3 section vertically up. Right? So then we can then kind of fold it across so that we have this one on the side. Right? This one would be on the side after we fold it up and fold it across. Just imagine that. So on the side here, we'd have a blank, and then we would fold down, right, this one here. So currently at this stage, imagine, we've got the bottom here. We've just folded up this whole section, right? So it should actually look like this. We've folded up an entire section, and we've got the corners looking a little bit like this, okay? Now, we then fold this side across, like I was saying, so that we get something looking like this. So we have this one already in place. We fold it across so we have this looking like this way. All right? And then we can fold this top one down, and that gives us a nice, also a blue triangle in here, facing the correct way. Okay? Now, for the last part. So this is going to fold up here, right? So we're going to get on the side, if we're just looking from the side there, if this is the base, and we've just folded that up from the side, we get something looking like this. Let me kind of show the fold. So you'd have something on the side looking like this, right? With the triangle looking on the bottom, actually, so that wouldn't really work. You'd see the triangle would be on the bottom, like here. And if you fold it across, not only would it be on the back face, so it wouldn't actually be on the right face, but it would also be just on the bottom, which we can't really have, okay? Now, if you fold up the net a certain way, there's no way of kind of rearranging the net to get different faces. So don't worry about thinking like, oh, I've just folded the net wrong, I've got to try a different way. No, that's not how cubes work. There's only one way of folding that net. Now, you can start with different things as the bottom, but once you actually folded it together, that's the only possible outcome, okay? So diagram 2 actually does not work. This one messes it up. Now, let's look at diagram 3. Let's create this one as the bottom. All right, so we've got this one as the bottom here. And so let me draw it kind of at a oblique angle. All right. So let's first start with folding this one up. So you'd fold those two up, and you'd have something at the back looking a little bit like, maybe like this. All right. A little bit like this at the back. Now again, the drawings in 3D are a little bit atrocious, but just bear with me. And so you'd have this triangle at the bottom here. And so you could fold that across so that you have something looking like, draw this a little bit better. Alright, something looking like this. So we folded this across, and you have something here with this black triangle here. Okay. Now, you can already see that this would not work because you'd need to have had a triangle on this bottom face here. Right? Because notice how it's angling in. You'd need to have one on that bottom face in order to create that vertex colored in all the way here. Okay? So diagram 3 also does not work. Alright? The vertexes would be separated. They wouldn't be on the exact same corner or facing the right way. So, Bit of a time-consuming question, but just needed some idea of that kind of spatial reasoning, being able to fold things in and have a look at what they look like. Okay? So we can see that diagram 1 was the only one that actually worked, so our answer there is going to be option A. Alright? Again, these ones are tricky to draw on a 2D page, so these ones really need you to invoke your, recruit your imagination and try and fold these in your head. Drawing little diagrams like this can help when you're looking, the progress, the stepwise process along the way of folding things, or should be the other way around, really. And you can kind of work out exactly how to get to each diagram, get to each shape from the nets. Alright, well anyway, that was question 18, all done and dusted. Again, let's have a look at question 19. So a bag contains 3 colors of disc, red, blue, and yellow. There are an equal number of red discs and blue discs. There are twice as many blue discs as yellow discs. One disc is selected without looking. What is the probability? Okay, so first of all, we should work out the total number of discs. Okay? So if red and blue are equal numbered, and there are twice as many blue discs as yellow discs, okay, then that means that yellow is going to be half of both red and of blue, because blue and red are equal. Now, the best way to kind of solve these questions, I'd say, is to give yourself a random number, all right? I call this random picking. All right? Cullen's random picking. And the idea is when you have just theoretical things of like having twice as many or half as many, whatever, just pick numbers that work and then find the probability accordingly, okay? So for instance, let's just say that there are, 2 red discs, 2 blue discs, right? And since there are twice as many blue discs as yellow ones, that means we only have 1 yellow, okay? Now, the question asks, what is the probability of selecting a blue disc? Well, now it's pretty easy to work out now that we have actual numbers. Right? We can say the probability of selecting a blue disc would be 2. Right? There's 2 possible blue discs out of the total. Right? So with probability, when you're trying to find the probability of anything, you're trying to find the the number of favorable outcomes, the things we want, out of the total outcomes. Okay? And so the favorable outcomes is 2. We got the 2 blue discs, and then the total is going to be 2, 4, 5. Right? It's going to be 5 discs. So the probability is going to be 2/5. Now, no matter what numbers you picked here, you may be wondering, like, well, what if we pick different numbers? The thing is it's about a fraction. It's about a proportion of the whole, right? So even if I made this, 4 red, 4 blue, 2 yellow, you'd still have 4 over 10, which would simplify to 2/5. So you can see here that the probability does not change based on the number of discs as long as you keep the proportion the same. So random picking can make it a lot easier to actually just calculate the probability using normal formulae, okay? So the answer there is 2/5. Or option D. Alright? So hopefully that there is making sense. Remember, random picking and giving yourself some actual numbers to ground yourself in reality can always be a helpful strategy. Alright, question 20. Here is part of a menu from a cafe. The prices have been torn off. A burger and a drink cost $6 in total. So burger plus drink cost $6. Chips and a drink cost $3.75. So chips plus drink $3.75. A burger, chips, and drink cost $8.50 in total. Burger, chips, plus drink, $8.50 in total. Okay, so how much does a burger and chips cost in total? Okay, well, what we can do here is we can realize, okay, we can actually find out how much each one is, right? How much a burger is and how much a chips is. Because first of all, we can say, okay, well, if burger plus chips plus drink equals $8.50. Well, we know that chips plus drink is $3.75, right? So we actually know that burger, by substituting this in, a burger plus $3.75, notice how I've taken this C and D, being $3.75 down there, equals $8.50. Alright, so the burger is just the difference between $8.50 and $3.75, which you can see would be $4.75, okay? So the burger would equal $4.75, alright? Now we can do the same thing for the chips, in that we can realize that, okay, well, let's rewrite this, right? Let's get rid of this highlighter. And we see, okay, well, we can find what the chips is based on the fact that we know that the burger and drink, right? Burger and drink is $6. Okay, so if burger and drink is $6, then that means that the chips plus the $6 has to equal $8.50. So you can see the chips are left having to be $2.50. Right? So just make sure you use your combinations to kind of almost substitute them in. And notice, okay, well, if burger and drink is $6, then burger, drink, and chips being $8.50 means that chips have to be $2.50. So we can see that the difference there, we can see the burger is $4.75. We can see the chips are $2.50. So let's try and find the burger and chips in total. We get $4.75 plus $2.50. So let's add these up. We get $7.25. Okay, so the answer there to question 20 is going to be option C, $7.25. All right, bit of a trickier one, needing to use that kind of substitutions, but hopefully it makes sense based on that. And yeah, hopefully we got that one. Good job if you did. So, question 21. Jason's clock was working normally until 7:05 a.m. At 7:05 a.m., he dropped the clock. For the rest of the day, the clock's hands turned twice as fast as normal. At 3:25 p.m. that day, what time did the clock show? Okay, so for the rest of the day, the clock actually turned twice as fast, meaning that the time that passed on the clock was actually 2 times as much as what actually passed. All right? So at 3:25 p.m., let's work out how much time has passed. We can then double it to see how much time would pass on the clock and work out the time. So from 7:05 to 3:25, let's work out the number of hours. So using 24-hour time is always a nice, easy way to do this. So 3:25 is 15, 25, and 24-hour time. You can see this is plus 8 hours to get from 7 to 15, and plus 20 minutes to get from 5 to 20. So 8 hours, 20 minutes is the amount of time that's actually passed. Okay, we need to find the amount of time that's passed on the clock. So on the clock, this would be double. The clock is moving twice as fast as normal. So this would be 16 hours and 40 minutes, just double of 8 hours and 20 minutes. So we need to put the clock 16 hours forward and then 40 minutes forward. So to go 16 hours forward, well, that would be going 12 hours. So back to 7 again, plus another 4 hours. So 1, 2, 3, 4. The hour hand would be pointing at 11. Okay? Now, the next one is 40 minutes. So that's pretty easy. From 7:05, the minute hand would just go to 45. You're just adding on 40 minutes there. Okay? So 45. All right, and so really the hour hand would be pointing a little bit more towards the 12. All right, so the time would be 11:45. Let's see which one lines up with this. We see option E does. Okay, 11:45. So just to summarize what we did, found the actual time that has passed. Then we find the amount of time that would have passed on the clock since it is moving twice as fast as normal. Then we can see what that would be, and option E lines up very nicely with the correct time. And so the answer to question 21 is going to be option E. All right, good stuff. Question 22. I have an equal number of $1 and $2 coins. The total value of my coins is $54. $1 coins weigh 9 grams and $2 coins weigh 7 grams. What is the total weight of all my coins? Okay, so we can see here that if the total coins is 54, then that means that we have a ratio of, in value, 1 to 2, right? However, there is an equal number of each one. Right? And so I think the best way to look at this is to see, okay, well, for every $1 and $2 coin, we have an equal number, right? So we're going to have a $1, $2 coin. We're going to have another $1, $2 coin. We've got to work out how many times this can add up to give us a total of $54. We've got to work out how much this adds up to give us a total of $54. So since each pair, right, is $3, well, we can do 3 into 54, and I'll kind of show you how this works in a second. So this goes in once, with 2 left over. 3 into 24 goes 8 times. So there's going to be 18 of these pairs, right? So that means 18 $1 coins and 18 $2 coins. Now, you could have worked this out by just trial and error, seeing which numbers would give you 54, okay? However, this is kind of a more systematic way of doing it, working out the fact that since there is an equal number, you have to do it in pairs, remembering the ratio that I showed you before of there being a $1 to $2, meaning this totals a total of $3 per pair, right? So, now that that's done, we've got the number of each coin based on the number of pairs of coins that we can put together to give us $54. We can work out the weight. So $1 coins weigh 9 grams, so that's 18 times 9 grams, and $2 coins weigh 7 grams, so that's 18 times 7. And we've just got to add those up. So let's do 18 times 9 first of all. Gives us 72. 9 times 1 is 9, plus 7 is 16. So we get 162 for this. All right. Then 18 times 7 56. 7 times 1 is 7, plus 5 is 12. So we get 126. Okay, now in total, this gives us 288 grams, which would be option B. Okay, so a little bit of a trickier one there, just in terms of that first step, in terms of adding up all those pairs, but really it shouldn't be too crazy once you've either used trial and error or used this idea of pairing up the equal numbered things to see how many lots of them you'd need. All right, so question 23. Two statues are 8 kilometers, 23 meters apart. A map maker incorrectly labels the distance between the statues on a map. The incorrect distance is 23 kilometers and 8 meters. What is the difference between the correct and incorrect distances? Okay, so we really need to just basically work out the difference between 23 kilometers, 8 meters, okay, and 8 kilometers, 23 meters. And I think the best way to do this is just use some decimals, all right? Now, we could go bit by bit, but I think the best way to do this is use decimals. So 23 kilometers and 8 meters is really 23.008 kilometers, right? Because think about it, right? And 8 meters in kilometers, if you want to find the amount of kilometers, you got to divide by 1,000. So you get 1, 2, 3. And so you have 0.008 kilometers being 8 meters. Okay? So 23.008 kilometers there. Now, 8 kilometers, 23 meters is going to be 8.023 for the same reason. You can move the decimal back 3 spots and you'll see you'll have 0.023. All right, now it's just, I suppose, a subtraction to find the difference between these, making sure we line up the decimal place and just minus like normal. Right, so we need to borrow a few numbers. All right, so 10 minus 2 is 8, 9 minus 0 is 9, 2 minus 8 can't do, so we borrow here. 12 minus 8 is 4, and we get 14, 985. So 14 kilometers, 985 meters, that's going to be option B. Okay, so when in doubt, when you have a mixture of different units, all put them into the same unit, all right? Same units here, and do your calculations like that, okay? So that is question 23. 24, Jetta draws a map of an island showing areas where there are only hills, only bush, or both. These 3 areas cover the whole island. Total area of the island is 164 kilometers squared. The total area where there are hills is 132. Okay, and the total area where there is bush is 80 kilometers. What area of the island has both hills and bush? Now, here's the thing, right? Is that this is a Venn diagram, really. Think about this as a Venn diagram. It's really a Venn diagram with extra steps, right? So this is hills. Let's call this hills. Let's call this bush, right? Now, when we are told that there is 132 kilometers in the hills, so 132, this is not just in this region here. This spans this region as well. Okay, meaning that it spans the whole circle where we have hills. That is 132. All right. Now, what makes this Venn diagram a little bit easier than other ones is the fact that there's actually there's no numbers on the outside, right? The whole 3 areas cover these whole islands, right? And so really, we can actually work out what goes in this non-highlighted section in here based on the fact that that green section has 132. So, because we have 164 in total, minus 132, we see that we get 32 in here, okay? So that totals up to 164. We can now work out how much is meant to go in each section. So, the total area where there is bush is 80 kilometers squared. Well, we have 32 here, so that means we have to put 48 in here to mean that we have a total of 80 in this blue section. I mean, not blue section, bush section, right? So that's a total of 80. Now we can work out, okay, well, in this section we'd have to have 132, so what needs to go in the only hills section with no bush? We can just subtract to work that out. Minus 48, so... Okay, so we get 12 minus 8 is 4, 12 minus 4 is 8, and so that is 84 there, okay? And now, what area of the island has both hills and bush? Okay, we didn't even need to work out the only hills section. It's just going to be 48 here, this one in the middle, all right? So, option C. Make sure you don't get confused. A lot of people would say, that this section here is 132 and this section here is 80, and that this section you got to work out yourself. That can obviously lead to some very quick problems. So make sure that you keep consistent with the fact that this is actually going for the hills and both. And this is for the bushes and both. Alright, important that you remember that whenever you're dealing with these kind of Venn diagram type questions. But yeah, option C there is going to be your answer. Question 25. A display has 3 lights that flash at different intervals. We've got the red light flashing every 2 minutes, green light flashing every 3 minutes, and the blue light flashing every 5 minutes. So let's draw these lights up. We can try and work out a pattern here. Okay. The question's asking between 7 and 10, basically, just within that. The same morning to whether the green and blue flash together how many times. When the red light is not flashing. That's the crucial part. The red light must not be flashing. So, I suppose the best way to do this is to work out a pattern, okay? Now, if the red light flashes every 2 minutes, now, of course, they all flash at 7 on the dot, right? And then the red light will flash at 7:02, okay? And then 04, and then 6, and then 8. All the even numbers, basically. Every single even number, right? So, if we want to work out when the red light is not flashing, we basically need to have, right? We must have an odd number. And that's the only consideration we need to take for the red light. Right, so we must have odd numbers. Any even number we can instantly rule out. Now, the green one, they're going to have multiples of 3. So 703, 6, 9, 12, etc. And now, think about it, right? When we get to 8 o'clock, that's the equivalent of arriving on the 60, right? Because you'd go 7:57, and then you'd go 8 o'clock. Okay, so that means that the cycle repeats itself. Right? The cycle repeats itself, starting at 7, going till 8, and then you see the same numbers would happen. 803, 806, 809, etc. Okay? Now, same with plays for the 5 minutes. The blue light, you've got 7:05, you've got 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, and you get 8 o'clock on the dot. Okay? Now, how many of these are also multiples of 3? Well, we'd have 15 as a multiple of 3, and that's odd, so that's fine. So it's not going to be when the red light's flashing. 30, while it's a multiple of 3 and 5, it's an even number, so the red light would also be flashing. 45 is the next one that works, and that's it. So we have 2 in the span from 7 to 8. So in the span of time from 7 to 8, there are 2 times flashes that satisfy this principle here. Now, the fact that we're going until 9:59 means that, well, think about it, right? These patterns here that we've created, they're going to repeat themselves, all right? Remember, like I said, it's going to start at 8, and then you're going to go 803, 806, etc., right? And you're going to have the exact same numbers, the exact same multiples. Just like here, you'll start again with 805, 10, and just like with the red light, you'll start again from 60 because it's a multiple of 2, and it'll be 802, 804. So each of these little segments, 7 to 8, 8 to 9, 9 to 10, they're all going to have the exact same number of coinciding flashes, which will be 2 in each of them. Okay? So 2 of them in each. So we just add those together. That gives us 6, right, in total between that period. Note that we're not counting 8 o'clock as one or 10 o'clock as one. So the fact of me writing there's 2 before 10 doesn't mean that, it's not excluding this 9:59 one, okay? So the answer is 6, all right? So just remember there's no flashes. The last flash would be 9:45, so it doesn't matter if we consider the end point to be 9:59 or 10. All right, so that is question 25. A little bit of a tricky one, but, finding patterns, identifying those, writing those out is probably the best way to go about it. Okay, question 26. 3 planks of wood all have the same length, and they are placed next to each other as shown. What is the length of one plank of wood? Now, with these questions, I think it's going to be much quicker to start with an answer. Have a look at one of the answers in the options. Usually start with the middle one is best, and if it's too long, you can know that the plank of wood has to be shorter, and if it's too short, you know the plank of wood has to be longer. Okay, so this is the specific way I do trial and error, so that it doesn't end up taking heaps of time. You'll only ever have to test 2 options. Okay, so for instance, let's try 60. And fill in what we know. So if each one is 60, remember they're the same length, right? If each one is 60, then that means that this has to be 20 centimeters here, right? And this would have to be 20 centimeters here, just based off this measurement here. Now, if this is 5 centimeters, then that means that this has to be 55 centimeters, all right? Now, we can add these up and see if they give us 135. Now, if it gives us more, say if it adds up to 150, we then say, okay, our planks of wood need to be shorter. So we try either B or A, and we can then determine exactly what the answer is, because if that works, if B works, for instance, then it's B, but if it doesn't work, then it's A. So that's how you can see what the answer is in exactly 2 goes or less. So, trying 60, that means that from here we'd have 60 centimeters from this plank here, Right? We'd then have, so that's 60 already done. We'd then have 20 in this range, and then we'd have 55. Right? So the total length should be 60 plus 20 plus 55, which gives us, oh, okay. We get the answer at first go, 135 centimeters. But I always recommend starting in the middle. Okay, so that it says that C works, but it doesn't mean that you're going to get the answer more likely first go. But it just means that, say we got, like I said, say we got 150, we'd go, okay, that doesn't work. Let's try 50 centimeters. What that would be, and that way, again, you only need to try 2. And then you'd put in 50 centimeters. You'd say, okay, this has to be 10. This has to be 10 as well. This has to be 45. Add them up, blah, blah, blah. And you can then find your answer, okay? But for this one, we ended up getting it first go, which was having, 60 centimeters working there. So that is question 26. All right. So, question 27. Alison shaded 3 small squares in the grid below. Right, these ones depicted. She wants to shade extra squares to make a pattern with exactly 4 lines of symmetry. What is the smallest number of extra squares she needs to shade? These ones can always be challenging because you don't know if you can find an example that works, but you don't know if it's the smallest number or if there's another way. But first of all, it's important to understand what 4 lines of symmetry is referring to. 4 lines of symmetry, well, the obvious ones that you can have in a square is this one and this one. That's only 2 though. The other 2 that you can have are these. So within a square shape, just based on the dimensions of the shape, you can actually only have 4 lines of symmetry. Because for instance, if I was trying to make a line of symmetry through like here or something, it wouldn't work just because the shape is not correct. So a square itself only has 4 lines of symmetry. So no matter what the pattern is, even if it's perfect, even if it's completely shaded in or completely blank, we'd still only have 4 lines. So we basically need to have all these lines of symmetry. That's what this is telling us. And so I think the best way to work through this is systematically ensure that we have each line of symmetry, right, given the already shaded shapes. So we have a line of symmetry here. Let's try and make sure that this lines up. Let's make sure that that serves as a mirror in between. All right. So shading in these shapes. And we can make sure that this is a line of symmetry here. So we just need to shade these, and now we've got that as a line of symmetry. We can move on to the next line of symmetry. You can see I'm not very good at coloring in the lines, but anyway. Now this line of symmetry, we would need to put in shaded circles, squares here. Right? And now that's a perfect line of symmetry, all good there. Now we need to go diagonal. And notice, again, if we want to reflect on this side, we'd have to have a square here. We'd have to have a square here as well as here. And here, just notice, basically, just treat that pink line that I just drew as a mirror and try to reflect it on either side. Now, we basically just did the least amount possible given these squares here, right, just to satisfy these 3 squares. So there's actually no, we haven't added any unnecessary ones. So this is the smallest number, right? Now I just need to count the amount of, and we can also see, by the way, that this line of symmetry here is also satisfied. You can see that it's reflected on both sides. Now, let's add the amount of squares that we've shaded. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the answer there's got to be D or 9. Okay, tricky one, but again, working through it systematically is always the best way. Question 28. Mirinda sold drinks at the class barbecue. The drinks were orange or lemon, and she sold 33 drinks altogether. Which of these statements cannot be correct? Okay, so for these, we just got to kind of come up with possibilities to either prove them right or prove them wrong. So she sold 10 more orange drinks than lemon drinks. Is this possible? Well, first of all, we've got to think of numbers that would work around that range. So, for instance, you could have 11 and 21, lemon and orange. Okay, and what would that add up to? That would add up to 32. Okay, so that's a problem. That's not going to work. And we can see that if we actually increase this by 1 more, 11 and 22, still we need to have that 10 range, right? Then this would actually give us 34. Okay, so it actually skips by 33. Turns out you would have to have an even number here, where 33 is an odd number. So actually 1, we can see it cannot be correct, okay? So this one's good. 1 cannot be correct. The next one, she sold twice as many orange drinks as lemon drinks. Well, we can actually see, well, for instance, if we sold 11 and 22 drinks, that's twice as many, right? And that would add up to 33 drinks in total. So we can see that one actually does work. So this is off the table in terms of not being correct. And then the last one, she sold 5 more lemon drinks than orange drinks. Okay, let's test this out. So again, we'd probably have a bit higher numbers, something like maybe 18 and 13, just make an estimate. You can see that that is a +5 difference, all right? And this would add up to 31. Okay, so we need a little bit more. So 19 and 14, that's also a +5, right? And that adds up to 33. Okay, so we do get 33 drinks if we distribute it like this. So again, this one's off the table. So the answer is statement 1 only. All right, that's the only one that cannot be correct. The others, we found possibles. Okay, we found possibilities that satisfy the other two. All right. Question 29. This shape is a trapezium with 2 right angles. Okay. And it has a square piece of card with side length 24 centimeters. So that would be a big shape, you know, like this big. Can't really draw it on this page, right? A big square, so 24 by 24. You can kind of plan it out already. Like this. All right. What is the greatest possible number of these trapeziums and I can cut out from this card? Okay. Now, the way we should approach these questions is to try and create tileable units. Right, now, obviously, we would be wasting space if we just put trapeziums side by side like this, okay? We would be wasting this space in here that we could be using for other trapeziums. So the best way to do this is to create a tileable unit that you can stack directly side by side. And the way that I can see doing this is, let me just show you by directly flipping this upside down. So I'll just outline this. And then what I'll do is I'll grab it and I'll flip it upside down. You can see that we could actually stack it exactly like this and it would fit perfectly into a rectangular shape. Right? Can you see how these are now tileable in that I can create lots of these new formed rectangles, one on top of the other. Right? Okay, so this would have a length of 6 centimeters here on the bottom and 2 centimeters here. So the rectangle is 8 by 3 basically. So how many times can you fit an 8 by 3 rectangle onto a 24 by 24 square? Well, you can fit the 8 length side 3 times along, and then you can fit the 3 length side 8 times up this. So I don't know if that's the right amount. 1, 2, 3, 4. I think it's 1 less. Okay, so you can fit 8 of them. So you can fit 3 by 8 of these rectangular tileable units. So 24 tiles. And there are 2 trapeziums in each tile. Alright, so 24 tiles equals 48 trapeziums in total. Okay? So, again, my advice, create a tileable unit that you can stack side by side and waste no space. Alright? Try to waste absolutely 0 space. Alright, very important. So you can see the answer there is option D. Alright. And so, yeah. Moving on, question 30, we can see Jamal makes a number sequence. He chooses the first number in the sequence. Then he follows these 2 rules, one after the other, repeatedly. Subtract 100, and then the next one is add 10. So each time this rule cycle goes, you know, you're minusing 100, the first step. Then you're plussing 10. So after each of these steps is done, after each pair of steps is done, you're basically overall, you're minusing 90. That's what's happening overall. Okay? Now, the 6th number in the sequence is 8,451. What is the first number in Jamal's sequence? So, if we think about it like this, right? 1, 2, 3, 4, 5, 6. The 6th number, each time you move forward, you're basically minusing 90 to get the next number in the sequence. Every 2 numbers. So, for instance, you'd have, first of all, you start with a number, you minus 100, then you plus 10, then you minus 100, then you plus 10. Okay, so the final one would be after minusing 100. Alright, and so we can just see that we basically, from here, this number to this number, you've actually just minus 90. From this number to this number, you've overall minus 180. So let's redraw our arrow. We've minus 180. So just working backwards and trying to work out then, okay. So that's minus 180, and then we've minus another 100. So you're basically minusing 280, alright, to get to the very end. Now, if the 6th number is, we're told is 8,451, and we're 280 minused away from the top number, well, we can just add back on that 280, and we can see what our final number, well, our starting number would have been. So let's add that up. And we get 8731, which aligns with option E. So E there is the answer, okay? So again, writing it out in a stepwise fashion, using these steps here, is really the only way that you can be sure, okay? So if we just relied on the minus 90 overall, alright, then that strategy wouldn't really work because we've got a minus 100 here without a plus 10 accompanied. So working out the fact that it's minus 90 every 2 and then fixing up the last bit by minusing an extra 100 to give us minus 280 was how we really did that question. Alright, question 31. A robot is facing southeast, okay, so northeast, southwest, so the robot is facing this way. right? It makes 58 quarter turns clockwise, then 93 quarter turns anti-clockwise. In which direction is the robot now facing? Okay, well, we could first of all rule out north, because if you're taking quarter turns, right? So let's draw a bigger plane so we can have a look at this. If you're taking quarter turns, you're only ever going to end up at one of these points here, all right? Because there's no way you're taking, you know, slightly more than a quarter turn or a little bit of adjustment. You're always taking a full quarter turn, meaning you're always going to be at an angle there, that kind of 45-degree angle between each of the angles, okay? So north is off the table. Now, 58 quarter turns clockwise. All right, so basically what we can establish here, right? So we start here, and we're making 58 quarter turns this way, clockwise. We know that every 4 turns, we're back to the start, right? We're back to southeast. So that means that after 8 turns, we're also back to southeast. After 12 turns, we're back to southeast, etc. Every multiple of 4, we're back to southeast. So what's the closest multiple of 4 to 58? Well, that would have to be 56, because that goes into 58 how many times? Let's check it out. Goes into 58 14 times. Okay, so that means that after 56 quarter turns, right, we will be at southeast, because we've reached back again to that starting position. All right, we'll be facing this way here. Then 2 more to make it 58. So 1, right, 1 and 2. So we'll be actually facing northwest. So this is where we're facing after our 58 quarter turns clockwise. All right. Then we're given 93 quarter turns anti-clockwise. So that's going this way. All right. Now, again, multiples of 4, we're going to realize are going to make our life a lot easier, because every multiple of 4 we start again at the original spot, which in this case now would be northwest. So the closest number to 93, I believe, is 92. Let's just make sure that 4 is divisible by 92. Yep, it goes in 23 times. So after 92 quarter turns, we're going to be back to northwest. Right? And then we've just got 1 more quarter turn clockwise, so we will go from northwest, anti-clockwise, to here, and so we will be facing southwest. So the answer there is going to be E. All right. So good job if you got that one. It really, again, a lot of these kind of things are about finding patterns, noticing where the pattern goes, and how many quarter turns and etc. Where the pattern, where there's every 4, you're back at the start, and using those, it really just wouldn't be sustainable in the time pressure of this test to be able to rotate 58 times, okay? So hopefully you didn't do it that way. Hopefully you used a little bit more of the problem solving to find the patterns. All right, but that was question 31. Almost done. Last few questions. So the shape is made from rectangles. Okay, so that means that all of these lines are straight lines and have right angles. That's something we can know, that it's made from rectangles, right? What is the perimeter of this shape? Okay, so the perimeter, as we know, is adding up all the sides. So let's just see what sides we can add up. This one here, 16. And I'll just go around anti-clockwise. So plus 14. Now, one thing I want you to realize is for these sides that aren't mentioned, if you have a look at these sides that I'm highlighting in orange here, right? If you added these all together, even though they're offset a little bit, you can actually see that they're still going to total to 16, right? Have a look. If I move this side directly inwards without even stretching it, you can see it's exactly perfectly the right size, right? We're not angling up. We're not angling down. That's why they said that there's rectangles. They're made of rectangles, because we're going directly at right angles. And so the actual length down that entire shape isn't changed. It's still 16, okay? So I'm going to add on 16 for that orange section, plus the 1 and the 1 of the kind of jut outs section here, this section here, and this section here. So we've done all the way around from here to here to here, down to here. Now the same thing applies over here, where if you notice the part that I'm going to color in purple, this bit, and this bit, hold on, this bit and this bit, they add up to 14, right? So we can add up a 14 there, and then we'll just add in the rest of the bits, 3, 3, and that's it. Okay. So now we just need to add these up. These add up to 30 here, 46, 47, 48, 62, 65, and 68. So the perimeter of the shape is 68 centimeters, or option E. All right. Okay, last 3 questions now. Let's move on.
Question 33. Timothy writes down the number 24. He reverses the digits to make the number 42. He then works out that 42 is 18 more than his starting number 24. Nicole writes down a whole number between 10 and 99. She also reverses the digits of her number. She finds that this makes a number that is 72 more than her starting number. Alright, so this kind of one here is a little bit of a trial and error type question. But we can guide this, right? We're obviously not going to have the numbers starting with, say, like 40s or something. We're not going to have the first number being like 45 or something. Because you notice that these are going to be too close, right? Say you had, like, even if you had 49, the extremes, it's too close. Same with 59 and 95 or 51 and 15. They're all too close. You can't get a full 72 range with two-digit numbers unless you're within the 10s and the 20s and the 80s and the 70s and the 90s, right? So let's start there, alright? Let's have a look at a number, say like 15 and 51. Obviously that's too small. It would be better to go for higher. So something like 18 and 81, alright? Let's have a look at the difference between this number here. So 81 minus 18, right, we get 63. So it's too small. That means we need to separate the distance even more. If we try to say 19 and 91, again, the lowest decade with the highest decade. Let's see if that works. Alright, so 91 minus 19. That gives us... Okay, that actually gives us 72. So we realize, okay, well, we found the numbers here. They're both between 10 and 99. Yep, filled that. So, okay. I guess it's just about experimenting, making informed guesses, realizing that, okay, we can't have the numbers towards the middle of the first 100 numbers, like 30s, 40s, 50s, because we just wouldn't have a range of 72 to work with there, within the two-digit numbers. Alright, because even 100 minus 72... Right, even 100 minus 72 is still going to be 28. So we'd need to have at least in the 20s or lower, right? So we found our numbers there. And yeah, so the last digit, I suppose, of this starting number would be 9. So E is 9 there. Okay. So, alright, that question done and dusted. Let's have a look at question 34. Harry has a large solid cube made from 64 small cubes. Okay, so we got 4 by 4 by 4, that makes sense. Alright, 4 by 4 by 4 is 64. And then he removes some of the small cubes, and he now sees this view when he looks at any of the 6 faces. So that's every single one of the 6 faces. He sees this view where this is empty all the way through. So we're actually not going to have any cubes in that center. Alright? So essentially what we've done is we've removed, first of all, the 2 by 2 block in the center. If you imagine you have a little block in the center of cubes there, that would, you know, would hinder any view through the cube. So we've got to first of all remove those 2 by 2 blocks. So that's 2 by 2 by 2. So that gives us 8 cubes. Right? We then would have to remove these 4 cubes here. Right? These 4 cubes. And then all the 4 cubes basically on all 6 of the sides. Okay? So we're just removing each of those so we have that window to look through. Alright, so on the bottom as well, move those 4 cubes that would be on the bottom there somewhere, and on the back here, and on the back here. Move 4 cubes that are blocking the view, and then all that we have left to remove, which we've just discussed, is these 8 cubes here in the middle. And then you'd have that hollow view looking through the cube from all of the faces. So, we remove 8 cubes, and then we remove 4 cubes from each face, there being 6 faces. That gives us 24 cubes. So, in total, we've removed 32 cubes. And since we have 64 in total, we can realize that we're going to have, in the object now, we're going to have 32 left over. Alright, which is answer B. Okay, so hopefully that makes sense. Again, it can be a little bit overwhelming to think about this, like, you know, when we haven't gotten information on everything, we're just kind of told about each face. But you can kind of piece it together, the fact that we'd have to be able to see all the way through to the other side, right, all the way down to the other side, all the way through, etc., etc. So yeah, that's how we work that one out, and then just work out how many you need to remove. The last question of the day. All right, let's make sure we get this one nice and easily, and if we can finish off. So Aaron and Tom have a game where they each spin this spinner once, and whoever spins the higher number wins. They play the game 8 times, and during the game, Aaron spins 2 1s, 3 2s, and 3 3s. Tom spins 2 1s, 5 2s, and 1 3. All right, so let's just lay this out. Aaron spins 2 1s, 3 2s, and 3 3s. Okay. Now, there are no draws, meaning that whenever I see, for instance, a 1, there can't be a 1 here. There has to be a 2 or a 3. Okay. We're then asked how many games does Aaron win. Now here's the thing, right? Is that the fact that we've been asked how many games does Aaron win mean that if we can find any working possibility, then it has to be the answer. Because there's not the opportunity to give multiple answers. Now I was mentioning this before. Whenever you see a question, right, where it's asking you to, find the amount of wins, you might say, how can I work that out? There's so many different possibilities. Find one possibility. If you can find a way that it works, that has to be the answer. Okay, because they can't have more than one answer. So that would have to coincidentally work for all possible combinations, or you've just found the only combination. So, let's just try and sort out with Tom's spins. Notice how Tom got 5 2s. Since this is a lot, we're probably going to have to sort these out first. Because have a look, right? We can't have the 2s overlapping in the middle here, because that would imply a draw. So the 2s have to be spread out across the other ones. So we have a 2 here, a 2 here. And that's the perfect amount of 2s if we fill in all the others. Now, it doesn't really matter. We have 2 1s and 1 3. So 2 1s and 1 3. This is a possible combination that works. There are no draws, and all the numbers fit. So let's count how many wins Aaron has. So there's didn't win this one, didn't win this one. This one he won, this one he won, lost this one he won, this one he won, and this one he won. So that is 5 wins in total, giving us option C to finish off. So, good work everyone. That was the test there. Hopefully you found this useful. So comment down below if you found it useful. If you have any other lasting questions, hopefully I explained these well enough. If you find you didn't really understand one of the explanations, try watching it again. Because, often watching something with fresh eyes after having seen some of the question can always help. But congratulations on finishing this test. If you've done it before, or if you're just doing it in some preparation for a future session, then congratulations nonetheless. It was a tricky test, but I'm sure each one of these was, doable from you guys. Anyway, I hope you guys have a lovely day, and I hope to see you soon. All right, all the best, everyone. Farewell.